Hello, and in this video we're going to be looking at the 2020 paper for Further Mechanics 1, the full A level, okay? And first of all, I want to look at the formula book to kind of give some guidance about how you can use the formula book, what will be relevant to tackle these sort of papers, okay? Okay, so with the formula book here then, so what parts of the booklet are going to be useful to us for Further Mechanics 1? Now, with Further Mechanics 1, you don't get given pretty much any formulas. So the formulas that will be useful, potentially, first of all, these trig identities, which are actually from pure maths, okay, from normal maths at year 2, from pure. These compound angle or double angle formulas for sine, cos and tan, okay. Particularly, you might use that with oblique collisions. Sometimes I want to do some sort of trigonometry with angles of deflections and stuff like that, okay. So that could be useful when you look at these sort of papers. And so if we now look at the mechanics section, well, the only mechanics formulas you have are the Suvat formulas, okay. And again, we don't really use that very often. Again, that's probably going to be most useful for when you're looking at collisions, when things are bouncing off the ground, okay. So we use Suvat there. Sometimes with the energy and power and forces sections as well. But yeah, so these are really the only the two main sort of formulas that are going to be relevant for FM1. Every other formula you're going to have to learn, okay? But luckily there's not many formulas in Further Mechanics 1. Okay, but if you're going to use with 2D collisions, with oblique collisions, you might have vector formulas. You're going to have to learn those. So for example, we might use that V dot W is U dot W and V dot I is minus EU dot I. So these are, for example, the formulas we can use for oblique 2D collisions with walls, okay? So you're going to need to learn them if you want to use them. So that's the formula book. Now, in terms of the instructions and information about the exam, most of it should be fairly familiar. Hopefully, if you practice or did some exam questions, it's going to be out of 75 marks. Usually, there's about 7 questions each in a paper. But the main thing you really need to pay attention to with mechanics is this bit here. Okay, obviously, you should know about G being 9.8. But what you might not know is your answers, unless they tell you to give it as an exact answer or in a particular way, you should give your answers to 2 or 3 significant figures. Okay, so if you want to round it, make sure you round it to 3 or 2 significant figures. Okay, that's probably the most important thing to highlight. Okay, that you might not be aware of, but there we are. That's pretty much everything. So let's have a look at the first question. So we got a fairly nice standard impulse question, and we can just use formulas, right? So we have a mass of 0.5 for this particle P, and it has a velocity of 4I and 3J. Then it receives an impulse. After receiving the impulse, it now moves with velocity minus I and 6J. So it wants to find the magnitude of J. So J is the impulse. So let's work that out. Okay. So remember the impulse formula with vectors is mv take away mu. Okay. Well, in this case, what are our vectors? Well, u, my initial velocity, is 4I and 3J, so I can write that as 4, 3. And V, my velocity afterwards, is minus I and 6J, so minus 1, 6. Therefore, I can use the formula to say that J, my impulse, is going to be the mass, which is 0.5. Lots of V, which is minus 1, 6. And then minus 0.5, lots of U. Okay. And so at that point, I can just simplify and calculate this. So that's going to be minus 0.5, 3, take away to 1.5. And so that will simplify to get me minus 2.5 and 1.5. Okay. So that's my vector, but it wants me to find the magnitude. So that's going to be this, right? So the magnitude, or the length of the vector. And so that's just going to be the Pythagoras of the components, right? So it's going to be minus 2.5 squared, add 1.5 squared, and then I root it afterwards. If I chuck that in the calculator, I get root 34 over 2 in exact form. Okay, so there we are. So that's my magnitude. Cool. Then it says the angle between the direction of the impulse and the direction of motion of P before receiving the impulse is alpha. Find the value of alpha. Okay, so what is this referring to? The angle between the impulse and the direction of motion before the impulse. What does that mean? It's referring to the initial velocity, because the velocity kind of tells me the direction, right? So it's referring to the direction between the impulse and the initial velocity vector. Okay, so it's going to be something like this, right? Let's, as an example, so we have my impulse vector there, and then let's say I have my initial velocity there. So the angle between them is just going to be alpha. Okay, now because we've got vectors, it's very nice. I can use the standard formula to work out the angle between two vectors from corporeal, right? So cos theta is a dot b over mod a mod b. So in this case, cos alpha is going to be j dot u over mod j times by the modulus of u. Okay, so if I substitute these, vectors in, well, j we worked out to be minus 2.5 or 1.5, dotted with u, which was 4.3. Then I divide by the magnitudes. Now for j, the magnitude of j, we work that out. It's root 34 over 2, right? So I don't need to do anything else there. Times by the magnitude of u, which is going to be the Pythagoras of 4 squared and 3 squared. Hopefully you can see that. And so I just need to simplify this. So it's going to be minus 2.5 lots of 4, and then 1.5 lots of 3. If I work out that dot product, okay, it's just from corporeal vectors. Then that's going to be root 34 over 2 times by root 5. It's going to be 5, right? And so just work all that out, okay? If I simplify all of that, I get cos alpha to be minus 0.377, blah, blah, blah. Okay, add some decimal. Then I can just do inverse cos. So alpha, if I do inverse cos of that, I get 112.166 degrees. Remember, we're in degrees. Usually with mechanics, it's degrees, not radians. So make sure you're in degrees mode. It doesn't say to round it to anything, so I'm going to round it to 3 significant figures. So that's going to be 112 degrees to 3 significant figures. And that's my alpha there. So just using the normal way we work out angles between two vectors from corporeal. And there we are. Okay, this question here. So we've got a truck of mass 1,200 kilograms on the straight horizontal road. At the instant when the speed is v, the resistance to motion is modelled as a force of magnitude 909 v. The engine is working at constant rate of 25 kilowatts. And so firstly, find the deceleration of the truck at the instant when v is 25. Now, deceleration is just basically acceleration, essentially, right? So find acceleration. Now, again, if we draw a diagram then, we are told that there's a truck on this horizontal road. So a horizontal road like that. So my truck's going to be on it like that, okay? The mass is 1,200 kilograms. And I'm also told there's a resistance force of 909 V, okay? So the resistance force, if it's going to move forwards, resistance will act backwards, okay? So we've got a backwards force of 909 V. But actually, we also are told V is 25, so we can sub that in right away. Okay, so when V is 25, resistance is 900, add 9 lots of 25, and so we can work that out as just a single number. So we get 1125 newtons. So I can just simplify that. Okay. Now there's also going to be a driving force that pulls it forward, right? And that is because we know there's a driving force because there's power involved. Because if you pay attention to this sentence here, working at a constant rate of 25 kilowatts, that tells me this is power. Okay, this 25 kilowatts, because I'm told work at a rate. The rate of work is power. Okay, so there we are. So we've got power involved, and remember the formula for power is speed times driving force. Okay, so because there's power involved, therefore driving force must also be involved, so a force acting forwards. Okay, so as I said, the power then is 25 kilowatts, but we need that in watts. Okay, so we need to convert that into watts. So remember, kilo is 1,000, so 25 kilowatts is going to be 25 times 1,000, which is 25,000 watts. Okay, so that's my power. So 25,000 is the speed, which we're told is 25 for V. Lots of the driving force D. So therefore, if we solve this for D, I'm going to do 25,000 divided by 25. And that will get me 1,000 newtons. Okay, that's my driving force D there. So I can add that on. Okay, so 1,000 here. Right, so now, remember, we want the acceleration. So, let's assume the acceleration is forward, right? Okay, it's moving forward. Okay, with an acceleration A. So I can just use F equals ma, right? So if I resolve horizontally, forwards and backwards, right and left, well, my forwards force in the positive direction forward is 1,000. Take away the backwards force, which we worked out to be 1125, and that's going to equal ma. So the mass, I'm told, is 1,200 kilograms. So 1,200, lots of A. Okay, so F equals ma there. And so if I simplify this, I get 1,200 A is going to be minus 125. It's a negative, which means it will decelerate. So that's fine. Now, if I divide by 1,200, I get the acceleration to be negative 5/48. Okay, and there we are. So again, deceleration means it's negative acceleration. So that answer seems to make sense there. Okay, then I'm told later on, the truck is moving up a straight road that is inclined at an angle alpha to the horizontal, where sine theta is 1/20. At the instant when the speed is v, the resistance is again 909 V. When the engine of the truck is working at a constant rate of 25 kilowatts, the truck is moving up the road at a constant speed v. Find the value of v. Okay. So what's different now is that the truck is on a road that's at an angle. So remember, that's going to look like a sort of ramp, a slope. So it's going to look like that. Okay. At an angle theta. Okay, so let's say the truck is, if I draw a little box here to represent my truck, again, the mass is 1,200 kg. So immediately what I can do is is add my forces. Okay, so with slopes, it's going to look like this. My weight acting straight down, which is 1,200 lots of G. Okay, mg. Okay, mass times G. But remember, with slopes, I'm going to want to resolve it like this as well. So we're going to go down here, then across there. So this angle is also going to be theta, which means that this is going to be 1200 G cos of the angle, and this is 1200 G sine of the angle. So those are the components for weight. Likewise, there will then be a reaction force we can add on like that, perpendicular to the slope. Okay, right. So again, there's still power. Okay, the power is still 25 kilowatts or 25,000 watts. Okay, so the power is still 25,000 watts. So I'm still going to need to consider the formula, right? That power is the driving force times the speed v. Okay, so therefore 25,000 equals dv. Okay, so I'm going to need to find d or v, right? But let's bear that in mind. Okay, I'm told there's a resistance force of 909 V. Now, I don't know what V is. It's a different V. So I'm just going to call it 909 V for the resistance force. So if it's going to go upwards, okay, up the ramp, resistance will act the other way to oppose it. So it's going to be 909 V. And again, because there's power involved, there's going to be a driving force D. Okay, which is going to be different in part A because the situation's changed. And that, I believe, is everything. The final thing to note is with the speed, it's constant, which means no acceleration. Okay, so acceleration is 0, which means the acceleration up the ramp is actually going to be 0 meters per second. And so with that in mind, I immediately now think about resolving using F equals ma. Okay, so we go up and down the ramp, while the force up the ramp is going to be D. And then the forces acting down, well, it's going to be this 909V. But also the weight component here, 1200 G sine theta. And that's going to equal 0. Right, because acceleration is 0. Now we could simplify this a little bit. So D, well, actually, if we look at this formula here, we can rearrange. We can rearrange for D because that'll get me V. So D, if I divide by V, is 25,000 divided by V. Okay, and so I can sub that into here. So D is going to be 25,000 V. 25,000 over V, sorry. Take away 900, take away 9V, take away 1200 G sine theta. Now, I'm told what sine theta is. It's 1 over 20, okay? I'm probably going to need to say G is 9.8 as well. So it's going to be 9.8 lots of 1 over 20 equals 0. So if I tidy this up, I get 25,000 over V, take away 9V, and then if I deal with the numbers, I get minus 1,488 equals 0. Now, how can I solve this for V? Well, actually, the fraction looks a bit scary, but I can just times everything by V to get rid of the fraction. Okay, every part of the equation. So 25,000 take away 9V squared, take away 1488V equals 0, and now it just becomes a quadratic. Okay, so there we are. So I'm going to get minus 9V squared minus 1488V, add 25,000 equals 0. So to show my working really quickly, if I just note down the quadratic formula, so it's going to be 1488 plus or minus the root of minus 1488 squared minus 4 lots of minus 9, 25,000 over 2 lots of minus 9. And so if I do that, put that in the calculator, or because I show my working, I can just quickly use the quadratic solver function on my calculator. I get V to be at 15.37, or V to be minus 180.70. Now, as you can guess, we're going to want to reject the negative solution. That's going to be because we're told it's a speed. Okay, V here is a speed. Remember, speed is positive. Okay, so that makes us only accept the positive solution. So, but I'm going to say, but V is a speed. So V has to be bigger than 0. Therefore, we can only take the solution V to be 15.4 to 3 significant figures. Okay, and there we are. And then we got this collisions question. So we've got two particles A and B of masses 3m and 4m. Particles are in the same direction when they collide. Before the collision, the speed of A is 2u and B is u. Coefficient of restitution is E, and first we need to show that the direction of motion is unchanged by the collision. Now, I'm not too sure how to get to that, but again, the standard thing with these questions, just do the normal method, right? So we draw a little diagram for our speeds before and after. So we have A and B. A has mass 3m and B has mass 4m. Now, initially, we are told they're moving in the same direction, so they're both going to move forwards like this, presumably. And A has speed 2u and B has speed u. Okay. Then afterwards, we're not told what happens afterwards, so let's just assume they both continue moving forwards. Okay. I'm going to call these speeds V1 and V2, okay, and so I can now apply the usual stuff with these sort of collision questions, apply momentum and restitution. So momentum firstly, so for A, the mass is 3m, lots of 2u, and then 4m, lots of u, then afterwards it's going to be 3m, lots of V1, add 4m, lots of V2. And so this will simplify to 6mu, add 4mu is 3mv1, add 4mv2. And then we can get rid of the m's, okay, cancel the m's out of all the terms. So we get 3v1, add 4v2 to be 10u, okay, and that's my first equation. Then restitution. Now, the straightforward way I like to calculate E is this formula here. So V2 take away V1 over U1 take away U2. So in this case, well, we have V2 and V1. We have V2 and V1 right here. So we're just going to take them away. Okay. And then U1 take away U2. So U1's 2U and U2 is U. So it's 2U take away U. Okay. Now, again, direction would matter, but everything's moving in the positive direction. So we can just apply the formulas as normal. So that will simplify to V2 take away V1 over U. Now, I'm just told E is E, right? I don't have a number for it. So I'm just going to leave it as E, okay? So for times across, I get EU is V2 take away V1, and that's my second equation there. So now I have these simultaneous equations. So minus V1 and V2 is EU, and also for momentum 3v1 and 4v2 is 10u. And so these are my two equations. The way I like to solve them, especially when the algebraic like this, I want to try and eliminate one of them. So if I triple the first equation, I get minus 3v1, add 3v2 to be 3eu. Then if I rewrite the second equation, hopefully you can spot how I can cancel out the v1s, because I can add them. The v1s will now cancel. So I get 7v2 to be 3eu, add 10u. And so then if I factor out a u, I get 3e plus 10. So that's 7v2. Therefore, divide by 7, I get v2 to be a 7th u of 3e plus 10. And so there's my expression then. Then to find v1, I'm going to sub v2 back into one of the equations. Let's substitute it into this one here. So minus v1 and v2 is eu. So therefore minus v1 add v2, which was this 7th u of e of 3e plus 10. That's eu. And then if I rearrange, I get v1 to be a 7th u of 3e plus 10 take away eu. Okay. Then if I expand now, well, actually, I can factor a u out of both the terms here. So it's going to be u lots of a 7th of 3e plus 10 take away e. So then if I simplify that part, I'm going to get 3 over 7th e plus 10 over 7 take away e. And so then if I simplify, I get u lots of minus 4 over 7th e, add 10 over 7. Then finally, I can factor a 7th out. So I get I'm going to get 10 minus 4e, and that's my expression for v1. Okay, right. So it says now show that the direction of motion of each of the particles is unchanged. Okay, so that's what we did, right? So we assumed that v1 and v2 indeed continue both moving forwards, which matches their original direction. So if we want to show that their direction of motion, their velocities are indeed not changed, they have to, these two numbers must be positive. Okay, because let's say if we had a minus 3 here for my velocity, that would tell me I'd have to reverse the direction to make it positive. Okay, I don't want to reverse the direction. That I want to say that they are continuing going forward. So both v1 and v2 must be positive to make sure I don't flip it. Okay, so I just need to show that v2 and v1 are positive. Okay. Well, actually, it's clear that v2 is positive. Okay, because e is positive, so v2 is positive as e is positive. Okay, and then for v1, okay, well, we are subtracting by 4e here. You might think, oh, you might get a negative, but actually think about it. E is actually between 0 and 1, so that means that 10 minus 4e must be positive. Okay, because the most e can be is 1, so the most we can do here is do 10 take away 4. Okay, but that's still 6, which is positive. So no matter what, 10 will outweigh and be bigger than 4e. So we're always going to subtract by a smaller number. Okay, so therefore v1 must be positive. Okay, because this bracket will ultimately be positive, and a 7th u is positive, so therefore v1 overall must be positive. Okay, by the way, u is always positive because u is a speed. Okay, so u so you see here they mention that the speed is u, so u is a speed quantity, which again must make it positive. Okay, anyway, so therefore we can say that since both v1 and v2 are positive, it must mean directions. It must mean that the directions of both the particles is unchanged. Okay, and there we are. Right, so now it's saying After the collision with A, particle B collides directly with a third particle C of mass 2m, which is at rest on the surface. The coefficient restitution between B and C is also E. Okay, so essentially we now need to consider this next collision between B and C. So if I draw that out, okay, so if I consider B and C now, so my second collision, which is between B and C. So B and C here. Now, as for the masses, B has mass 4m and C has mass 2m, okay? And I'm told that C is at rest, right? So initially C has 0 speed. So C has mass 2m and it's at rest, so originally 0. And B has mass 4m. Now, as it goes into the second collision, it's gonna maintain its speed after the first one, which was v1, right? V2, sorry, wasn't it? Yes, after the first collision, B leaves off with v2. Okay, so that's the speed it's gonna have here. Then afterwards, well, let's say that both B and C move forward, okay? So I'm going to call these W1 and W2. And again, I'm going to use the same techniques of restitution and momentum. So momentum, so that's going to be 4m lots of V2, and then 2m lots of 0. It's going to be 4m lots of W1, add 2m lots of W2. So that will simplify to 4mv2 to be 4mw1 add 2mw2, and then we can cancel the m's, right? And so we're going to get 4w1 add 2w2 to be 4v2, and actually we can further cancel by 2, okay? So we get 2w1 add W2 to be 2V2. And so then we can also use restitution. So that's going to be E, which again is V2 take away V1 over U1 take away U2, which is my standard formula. So in this case, we have W2 take away W1 on the top. And then on the bottom, U1 take away U2, well, it's going to be V2 take away 0, right? And so again, it's still E, so it's going to be EV2 is W2 take away W1. And so I'll get these two equations. And so now I've got simultaneous equations. So W2 take away W1 is EV2. And also for momentum, 2W1 and W2 is 2V2. Okay, and there we are. Now, actually, before we now proceed to solve, we can be a bit particular. We can be a bit smart about what exactly we can do here, because ultimately the question wants me to show if there will be a second collision between A and B. So actually, I only need to consider what's going to happen to B. I don't care about what happens to C. Okay, so I don't actually need to find W2, which is the speed for C. I only really need to find W1, so I don't need to go the full way and solve for both of them. I just need what W1 is, okay, which is for B. Okay, so I'm only going to solve for W1, so I'm going to eliminate W2, which I can do quite easily because I can take these away. Okay, so that's going to get me minus 3W1 to be EV2 take away 2V2, so that'll be V2 lots of E minus 2. Therefore W1 divided by minus 3, get minus a third V2 of E minus 2. Now actually I can sub in what V2 is. Okay, remember from part A, V2 was a 7th U of 3E plus 10. a seventh u of 3e plus 10. And so if we simplify that, we're going to get minus 1 over 21 u lots of e minus 2 3e plus 10. And that is my expression for w1, the speed of b afterwards. Okay, so again, as the question said, it wants me to consider what happens to a and if there's going to be a collision between a and b. So what I'm going to do to help me see that is I'm going to draw a diagram after the collisions for a and b. So I'm going to do it like this. So this is my final diagram after the collisions. So again, I just want a and b. I'm not even going to add their masses. I just care about what the speeds are. So for A, what's the final velocity for A? Well, it's v1 here, right, after the first collision. So it's going v1 forwards, which we established is positive, and B is as we also discussed, is going forwards with w1. And there we are. Now, what we need to do is show that there will be a second collision between A and B. Now, because we draw a diagram like this, it should be fairly clear to see when that will happen. So, if both of them are moving forwards, okay, well, clearly, if there's going to be a second collision, A has to be faster than B in order to catch up to it, right? So that means if there's a second collision between A and B, that means that the speed of A has to be bigger than the speed of B, okay? Because then A will catch up to B and then hit it, okay? So that means that V1 has to be bigger than W1, okay? Now, I should clarify, we do know for certain A is moving forwards with V1 because V1's positive. We discussed that in part A. A must be going forwards here, okay? But B, we don't really know what W1 could be. It maybe could be going backwards. I'm not sure. But that's irrelevant to me because if B was going backwards here, if W1 was flipped, that's basically irrelevant because they're both going to collide by default because they're both going towards each other. You can see that, right? Their directions going towards each other. So I don't need to consider that. So I only need to consider if it's going forwards as well. So they have to catch up. A and B have to catch up to B. So I just need to consider V1 being bigger than W1. Okay, hopefully happy with that. So if I substitute my expressions in, V1, V1's here, right? V1 is a seventh u of 10 minus 4e. So if I substitute that in, and so that has to be greater than W1, which was this expression here. So minus 1 over 21 u of e minus 2 3e plus 10. And so at this point, effectively, I just have to deal with this inequality. So I should probably try and solve it. And the first thing I can do is divide and cancel the u's, right? So that'll become a seventh of 10 minus 4e bigger than minus 1 over 21 of e minus 2 3e plus 10. Okay, again, I'm divided by positive quantity, so I don't need to reverse the inequality because u is positive, u is a speed. Okay, then I can actually get rid of the fractions by multiplying by 21 to both sides. So 21 over 7 is 3, lots of 10 minus 4e is bigger than minus e minus 2 3e plus 10. I think at that point I should probably start expanding the brackets. So 30 minus 12e on the left, it's going to be bigger than minus, then it's going to be 3e squared plus 10e minus 6e minus 20. And so then if I expand that out with the negative, I get minus 3e squared. Then it's 10e minus 6e is 4e. So then negate that. That's going to be minus 4e minus plus 20 if I negate that. Okay. So hopefully happy with that. And so now if I move everything to the left, I'm going to get 3e squared. And then minus 12e, add 4e is going to be minus 8e. And then 30, take away 20 is going to be plus 10 is greater than 0. So now have a sort of standard quadratic inequality to solve. So if it was to solve it in a normal way, okay, so solving this quadratic inequality, okay, well, what we do is again find the critical values, right, before we sketch it. So the critical values are when you just solve it equal to 0, right? If he was to solve it, okay, you get imaginary roots, okay? So there are no real roots, okay? If you were to put that in your calculator, you get imaginary roots, so no real roots. Again, you can confirm that because if we work out the discriminant, that's going to be minus 8 squared minus 4 lots of 3 lots of 10. That should be negative, okay? Yes, you get minus 56, okay, which is less than 0. So you can justify there's no real roots. So actually, the graph won't cross the axis, and it's going to be a positive quadratic, so it's going to be something like that. So we can see it's going to be always bigger than 0. The graph is always positive. So 3e squared minus 8e plus 10 is always bigger than 0, okay, for all values of e, okay? And so the inequality must be satisfied, right? So remember, that means that V1 is bigger than W1. So that has to be true, right? Because that's what we got here. So therefore, indeed, V1 must be bigger than W1. And so that means, because we discussed, that means A will catch up to B, and so they will collide. So A will catch up to B and collide again, okay? And so there we are. Right, now the other way you could do this, obviously that's sort of, I guess, the more automatic way is to sort of solve the inequality, as you know, from GCSE or from normal maths. The other way you can prove this quadratic is bigger than 0 is by completing the square, okay? Which is a bit more elegant, I think. So if we was to complete the square on this, so if we factor the 3 out, we're going to get e squared minus 8 over 3e plus 10 over 3. Then if we proceed to complete the square, we're going to get e minus 8 over 6, okay, squared, and then minus 64 over 36 plus 10 over 3. Then if we simplify, we're going to get 3 lots of e minus... Now 8 over 6 will go to 4 over 3. Okay, not that that matters, but we can simplify that. Then if we expand that bit, we get plus 14 over 3 at the end here. Okay, if we expand all that out, and that should be the completed square form. Now, you can see that because we've got a square number here, that's always going to be at least 0, okay, for any value of e. But also then we're adding by a positive number, okay. So we're adding two positive numbers, so we get a positive result. So that means it's also greater than 0, okay. So we can see that 3e squared minus 8e plus 10 has to be at least 14 over 3, which is bigger than 0, okay? So therefore the inequality is also always above 0 for all values of e. And so again, it's that sort of idea that therefore that v1 is bigger than w1, so a will catch up to b and collide again. So therefore, so there we are. Okay, so ultimately, you should be able to conclude that in any case, any value for e, no matter what, the inequality will be satisfied, and so indeed a will have a bigger speed than b, allowing a to catch up to b, and they collide once more. But there we are. Okay, so we've got this question here. So we have this diagram, right, and we're told a small ball of mass 0.5 kg strikes the wall. Before the impact, the velocity is 7i and 2j, which you can see there. Afterwards, the velocity is I and 6j. Coefficient restitution is E, and so we need to show that the AB, which is actually the wall here, the wall AB is parallel to the vector 2i and 3j. So when you're dealing with oblique impacts like this, with vectors, we can use the vector formulas, right? So remember, that's going to be that v dot w is u dot w, and also v dot I is minus eu dot I. By far, I think it's the best way to tackle these questions, and you should get the marks for that, okay? Mark schemes these days will factor this method in. Now, if we now state what our vectors are then, okay? So what is u, v, w, and I? So u, first of all, that's going to be my initial velocity, which, as you can see here, is 7i and 2j, so 7, 2. V is the velocity afterwards, which is going to be I and 6j, so it's going to be 1, 6 as a column vector. Okay, then W, well, that's what we want to work out. We want to work out the what the wall vector will be, right? So then what about I? What about my sort of impulse vector? Okay, now we're not given an impulse vector, but we can work one out because we know what the mass is and we know what the two velocities are. So remember that I can work out by doing mv take away mu. Okay, and so I can work out my impulse vector like that. Now the mass m is 0.5 kg. So it's going to be 0.5, and then if I factor that out, I'm going to get v take away u. And so if I sub in my two vectors for v and u, so it's going to be v, which is 1, 6, take away u, which was 7, 2. And so that's going to be 0.5, lots of the vector. 1 take away 7 is minus 6. 6 take away 2 is 4. So that'll go to minus 3, and then 2 there. And there we are, that is my impulse, okay? Now, remember the question wants me to show that AB, the wall AB, is parallel to this, okay? So it has the same sort of direction vector, right? So, remember impulse then is always perpendicular to the surface. So impulse here, perpendicular to the wall AB. Okay, so impulse has to be perpendicular to the wall. Okay, so if you think about it then, if this is the vector AB, then there have to be perpendicular vectors, right? So if we want to show AB is parallel or in the direction of this vector, there has to be perpendicular to the impulse vector. So how can we show two vectors are perpendicular? We can show their dot product is 0. So if I do my impulse vector dotted with the vector for the wall, which they told me is 2i and 3j, which is 2, 3 as a column like this, well, that will go to minus 3, 2 dotted with 2, 3. Then if we work out this dot product, we're going to get minus 3 lots of 2 and then 2 lots of 3. That will go to minus 6 add 6, which indeed is 0. So therefore the dot product is 0, so the vectors are parallel. So I, or the impulse, is perpendicular 2, 2, 3. Okay, and so I'm going to say that since impulse is perpendicular to the wall, then the wall AB must be parallel. It must be in the same direction as this vector. Okay, and there we are. And in part B says find the value of E. Now that's fairly straightforward because now I can use this equation because I know what V, U and I are. So I can easily sub that into this equation to get E. So, so part B, so V dot I is minus EU dot I. So if I substitute V, U and I in, so V, remember, is 1, 6, okay? So 1, 6 dotted with I, which was minus 3, 2, is going to be minus E, lots of U, which was 7, 2, dotted with I, which was minus 3, 2. And so I can sort of work out these dot products and solve for E from there. So if I work out this dot product, that's going to be 1 lots of minus 3, add 6 lots of 2, is going to be minus E lots of, then if I work out this dot product on the right, it's going to be 7 lots of minus 3, add 2 lots of 2. So now if I simplify, I will get 9 on the left is going to be minus E lots of minus 17. And so minus E times minus 17 is 17E, which is 9. Therefore E, very nicely, is 9 over 17. And there we are. Right, and now I've got this question here. So I'm told a smooth uniform sphere P has mass 0.3 kilograms. Another smooth sphere Q with the same radius has mass 0.2. Spheres moving on the same horizontal surface, they collide obliquely. Before the collision, P has velocity 4I and 2J, and Q has minus 3I and J. The line of centers is parallel to I. Kinetic energy of Q is half the kinetic energy before the collision. Okay, so it wants me to work out velocities and stuff like that. Now, actually, these are, so what we have here, right, is oblique collisions with two spheres. Now, because it's in vector form, it's really nice, because when we're dealing with vectors with 2D collisions of two spheres, we can literally just use formulas. I don't even need to draw a diagram, okay? The equations will tell me everything, okay? So I can use the equations. So if I just list my velocities, right? So firstly, for P, the initial velocity for P, we are told is 4I and 2J. So it's going to be 4, 2. And then for Q, the initial velocity is minus 3I and J. So it's going to be minus 3, 1. And then what about afterwards? So what about the final velocities? I'm not told any final velocities, right? So for P, now I'm parallel to I. Now remember, with oblique collisions, everything acts along the line of centers. Everything acts parallel to the line of centers. So if everything is parallel to I, then J has to remain the same, right? So my J components have to remain the same. So for P, if the J component is 2 before, it's still going to remain 2 after. Likewise for Q, the J component is 1, so it's still going to remain 1, okay? So it's going to be just the I components that change, because remember, everything that's important acts parallel, okay, to the line of centers. In this case, I'm parallel to I, so I need to look at my I components. So I'm going to call the I components A and B respectively. So I just need to find A and B to find my velocities. Now, again, the question is mentioning being parallel to I, the line of centers, right? So we just need to consider the I components, okay? And so what I'm going to do now is momentum and restitution, but just for the I components. So firstly, momentum. Now for P, the mass is 0.3 and Q is 0.2. So it's going to be 0.3 lots of the initial I component, which is 4, and then 0.2 of the initial I component of -3. Then afterwards, it's going to be 0.3 lots of A, and then 0.2 lots of B. So those are my I components. Okay. So if I simplify this, I'm going to get 0.6 is going to be 0.3A add 0.2B, and so I get this equation here. Okay. Now I would then proceed to use restitution, but I don't have any information about restitution. In fact, it wants me to do that in the third part of the question, so I can't do that here. But what I am told is stuff about the kinetic energy, so I'm going to need to use that instead. Now I'm told the kinetic energy of Q after the collision is half the kinetic energy before. So if I just write that down, so for Q, the kinetic energy afterwards is a half of the original kinetic energy, so the kinetic energy before. Now remember, kinetic energy is a half mv squared, where v is my speed. Okay, so if I'm going to work out the kinetic energy before and after, I'm going to need to work out the speeds involved. Okay, so I'm going to do them here. So speed before. Okay, well, what I am told is I'm not told any speeds, but I am told the velocities, right? So initially, before, the velocity for Q is -3,1. So I'm going to work out the speed of that. So it's going to be the Pythagoras, or the modulus of that, right? So it's going to be the modulus of -3,1. So it's going to be the Pythagoras of -3 squared and 1 squared, which should be √10. Okay. Then if I work out the speed afterwards, so that's going to be the modulus of my velocity afterwards, which is b1. Okay, so that's going to be the modulus of b squared and 1 squared, which is just b squared and 1. Now I can't do anything more to that, but I'm going to leave that there. So now I can work out the kinetic energies involved. Okay, so the kinetic energy before is going to be half lots of the mass of Q, which is 0.2, lots of the speed squared. Now before, the speed is √10, and so I'm going to square that. If I work that out, I get 1. Okay, then if I work out the kinetic energy afterwards, that's going to be half lots of the mass, 0.2, and then the speed afterwards of √b squared and 1. Then I square that, so that's just going to be b squared and 1 lots of 0.1. And so if I simplify that, that's going to be 0.1b squared add 0.1. So now I have my kinetic energy before and after. I can substitute it into here, this sort of formula we've got. So kinetic energy afterwards, so 0.1b squared add 0.1 is going to be half of the original kinetic energy before, which was 1. Okay, so therefore 0.1b squared add 0.1 is going to be 0.5. So we solve for b, we're going to get 0.1b squared, it's going to be 0.4. So therefore b squared, if we divide by 0.1, we get 4. So therefore b has to be plus or minus 2. Okay, right, so which of these two solutions do I take then? Well, I'm probably going to have to do a little diagram then to help me show which solution is valid. So if I just consider the parallel speeds, okay, because obviously that's what I really care about here. Okay, so P and Q, right? So the parallel speeds, so for P is 4i initially, so P is going to the right by 4, and Q, the I component initially, is -3i. So that's going to the left by 3, right? Because that would be -3i, because negative going to the left or backwards. So hopefully happy with that. So then afterwards, well, Q, well, we said that the I component was B, right? That's what we want to work out. So it's going by B afterwards. But as we just discussed, B could be plus or minus 2. So if it was, if B was plus 2, that will tell me indeed it's going to the right, forwards. But if B was minus 2, I would have to then reverse the direction, and actually it'd be telling me I'm going to the left, backwards instead. Now, if we think back to 1D collisions, because that's what we've essentially got here, can this make sense? Not really, because that would most likely mean Q would have to pass through P. But if you think about it, you're gonna have to like phase through P, right? You can't get around P. You can only get through P, but you can't pass through the particle, right? That makes any sense. So you get a nonsensical situation when you say Q is going to the left. Now, what could happen is P could also go to the left, and P could be faster than Q. So Q wouldn't have to pass through P. So we need to justify this further by working out if Q is going to the left by 2, what would P go by? Well, actually, P. Remember, for P, the I component is A. So I just need to work out A, right? So let's say B was well, B would have to be minus 2, right? If it was going to the left by 2. Okay, that makes sense, because that's in the negative direction. So it'd be minus 2i. Anyway, so if B's minus 2, let's go, we can work out what A would be using this equation, right, for momentum. So if B's minus 2, then A, well, 0.3A would be 0.6 minus 0.2 lots of minus 2. And so 0.3A would be 1. So therefore, A divided by 0.3 would get 10 over 3. So A is positive in this case, right? So that's telling me if B is minus 2, which tells me Q is going to the left by 2 afterwards, A is positive, it'd be 10 over 3. So actually it'd be going to the right by 10 over 3, because that's the positive direction. Now, that's what we've got. If B is minus 2, this is the situation we've got where Q has to go into P and P will go into Q. That just physically can't make sense. They're going to go into and pass through each other, which can't happen, right? So B cannot be minus 2, clearly. Okay, Q cannot be going to the left. It can't. So the only thing it can do is go to the right. So B would have to be a positive number. Okay. So there we are. So what I'm going to say to justify my answer is, but B cannot be minus 2, because then A would be 10 over 3, which would mean that P and Q would have to pass through each other. Which obviously would make no sense. Okay, so it's which is nonsensical. So therefore, we can only accept B to be positive 2. Okay, and that is my only solution there. Okay, and so hopefully they made sense. Okay, so Q essentially can only go forwards to the right in the positive direction. Okay, so B can only be positive 2. Can't go to the left, can't go backwards, so B can't be negative 2. Right, and so therefore we can immediately find the velocity of Q, because Q is B1. But we know that B can only be 2. So VQ, the velocity of Q afterwards, is B1, which has to be 2, 1. And there we are. And actually, now we can find A, okay, when B is 2. Okay, so we can find A using the same momentum equation, right? So 0.6 is 0.3 A and 0.2 B. But because B is 2, we can work out what A is. So 0.3 A is going to be 0.6, take away 0.2 lots of B, which is 2. So that will get me 0.2. And so therefore, divide by 0.3, I get A to be 2/3. Okay, and so therefore I can work out the velocity of P. Okay, so VP. Now remember, VP we said was A2, I believe. Yep, A2. But we know what A is, so I can sub that in directly. So 2/3 2 for my velocity for P afterwards, and there we are. Right, so hopefully you're with me here. So now it wants me to work out the coefficient of restitution between P and Q. Okay. So at that point, so again, I can apply restitution to my I components. All right. So I remember that A is 2/3. Okay, and B was 2. So E, if I just do it here, remember that that's going to be V2 take away V1 over U1 take away U2. Now, if I just look at the I components, V2 is 2, V1's 2/3, so 2 take away 2/3. Then U1 is 4 and U2 is -3. So 4 take away -3. So E is going to be 4 over 21 if we work that out. And there we are, my coefficient restitution there. Part B is asking to find the size of the angle for which the direction of motion of P is deflected. So that's referring to angle of deflection. Okay. Now, again, because we're dealing with vectors, it's quite nice. I can use the formula that cos theta is A dot B over mod A mod B, like I did with question 1. Okay. To easily work out the angle deflection there. So P, it wants the angle deflection, so it's going to be the angle between sort of the initial velocity UP and the final velocity VP. So this angle deflection here, theta. Okay. Now, if I just sub in what my velocities are, so 4, 2 and 2/3 2. So to work out the angle between these two vectors, which will get me the angle deflection, I could just use the formula cos theta. It's going to be the dot product of these two vectors divided by their magnitudes. Okay, so if I just work all that out, that's going to be 2/3 lots of 4, add 2 lots of 2 divided by the magnitude, so 2/3 squared, add 2 squared times by 4 squared and 2 squared. So at that point, if I work all that out, I get root 2 over 2, so that's going to be cos theta. Therefore, if I do inverse cos of that, I get theta to be at 45 degrees exactly. And that is my angle deflection there. And so then we have this question. So we have a light elastic string, natural length L, modulus of elasticity kmg, has one end attached to a fixed point A on the rough plane. The other end is attached to a package of mass m. The plane is inclined at an angle theta, where tan theta is 5 over 12. The package is initially held at A. Package then projected with speed root 6gl up the line, and first comes to rest at point B, where AB is 3L. Coefficient of friction is 1/4. And so we need to show that k is 15/26. Okay. Right. Okay. So ultimately what we've got then is, again, this sort of sloped plane, this sort of ramp, right? Because we're at an angle theta. Okay. So it's going to look like that. Okay. Right. So the string's going to be on the ramp then, right? So this is a sort of string problem we're going to be dealing with here. So we're told this package, this particle on the string, is going to go up the slope. Okay. So we're going to have our string here, right? My fixed point, the one end of the string, and then the particle's going to go moving up the ramp like that. Okay. Now, so I'm told that A is the fixed point. Okay, so A is going to be the fixed point here. I'll call that A. I'm told the package is initially held at A. So actually the particle, the package, is literally at the fixed point. Okay. Then I'm told the particle, the package, goes up the slope and then comes to rest at the point B. Okay. So if I draw that on a separate diagram, down here, then it's going to reach the point B. Okay, so the particle is going to go up the ramp like that. Then it's going to reach a point B. Okay, and so what I have here then is sort of a before and after diagram, right? So it starts at the point A. This is going to be like my before diagram, and then at the end, afterwards, it reaches point B. Okay. So what I could do actually is consider the energies, right? The energies involved between the before and after. Okay. So if I add the information on from the question, firstly, I'm told the package is projected from A with speed √6gl. So I can label the speed here to be √6gl, and then I'm told at the point B it comes to rest. So the speed at B is going to be 0. Okay. So that's my speeds. Now what about distances? I'm told A to B is 3l. So here, this length is going to be 3l. Okay, hopefully you can happy with that. But I'm also told the natural length is L, so I can add that on. Okay, so if I split this little string up, this is my natural length, and then you can see the extension is 2L. So what I'm then going to do is label my extensions, because I'm going to need that with the Hooke's law or the elastic energy formula. So the extension is 2L here. Now what about here? Now you probably might think it's going to be a compression, right? If the natural length is L, you might be tempted to think here the compression is all the way, so it's going to be L for the compression, but I'm told it's a string. Now the key thing you need to know with strings compared to springs, strings cannot be compressed. Okay, if you were to try and compress it, it would actually just go all floopy. It won't actually shorten its length. It will just go all floopy or slack, right? So actually, it looks like there is compression, but actually there isn't, because you can't compress a string. You can only stretch it. So I'm going to say that there's no compression, okay, or extension for that matter. Okay, so there we are. Now, what I also need to consider is there's also friction involved here, right? It's a rough plane. And also it mentions coefficient of friction. So there's going to be friction, right? So obviously I'm going to need to then use the work energy principle. Okay, because there's going to be sort of a force involved, right? So friction here, right? Now, if the particle is going to go up the ramp, friction will oppose it. So there's going to be a friction force going down the ramp like that, okay? So there's my friction force there. So I'm probably going to need to work that out, alright? I can do that because if I, again, now do the weight components, And I can work out the friction here because I got my coefficient of friction, right? Coefficient of friction mu is a quarter. And so I can work out the reaction force and then do F equals mu R, right? So if I split up the weight component, okay, here, well, the weight is mg, I believe. Yep, the mass is m, so mg. So if we split the components up, that's going to be mg cos theta there, and then mg sine theta, and then we're going to have a reaction force R. So if I resolve perpendicular to the slope like that, so it's going to be R is going to be then this component here, okay, mg cos theta in the other direction, and there we are. Now we can work out what cos theta is because we know what tan theta is. It's 5/12. Now what we can do with that is we can do a little triangle. Okay, we don't need to work out theta explicitly because we just need cos. So theta, okay, so remember, think back to SOHCAHTOA, tan is opposite over adjacent, which means the opposite length is 5 and the adjacent is 12. So the Pythagoras, right, the hypotenuse, 12 squared and 5 squared is 169. So we get 13, okay, when we root that. And so therefore, we can see that sine theta then, firstly, well, that sine is opposite of a hypotenuse, so 5/13. And then cos, which is what we want, is going to be the adjacent over hypotenuse. And so there we are. So cos theta is 12/13, so I could sub that in. So therefore, my reaction force is just 12/13 mg. And now we can work out what friction is, F, because F is mu R. And so that's going to be a quarter for mu, lots of this 12/13 mg for R. If we work that out, that simplifies to 3/13 lots of mg. And that's my friction force. Okay, now I think we're in a position to apply the work energy principle. Okay, so how I like to do the work energy principle is this formula here. So I look at all the change in the energies, right? So the change in kinetic energy, and then the change in gravitational energy, then the change in elastic energy is equal to what I call the overall work. Okay, and that's my work energy principle. So I'm just going to work all these bits out term by term, bit by bit. So firstly, the change in kinetic energy. So that's going to be half lots of the mass. And so the change in kinetic energy is always going to be the final minus the initial. So obviously that's going to be speed squared, because remember, kinetic energy is a half mv squared. So we need to take away the final speed from the initial speed to get the energy, to get their kinetic energies, right? So in the final part, okay, in the after diagram, the speed, as we can see, goes to 0, goes to rest. So it's going to be 0 squared at the end, and then initially we saw that the speed was root 6gl, okay? So it's going to be root 6gl all squared. So that gets me my change in energy. So always, when you work at change in energy, it's always final, take away the initial part of that, okay? In that order. So if we work that out, that's just going to be a half m, lots of minus 6gl, right? And so that'd be minus 3 mgl. Okay, the negative is important. That tells me we're going to lose the energy, but that's fine. The physical change is a loss, okay? So I must keep the negative, okay? Then the change in gravitational energy, GPE, well, that's mgh, okay, with the vertical height h. Okay, where's the vertical height? Okay, if I get rid of all of this, we can see This is my height h, okay? So to work out an expression for this, well, again, we're going to need to consider this sort of triangle, okay? So this is h, this will be theta. Now, this distance is the physical distance we've moved up the slope, right? That's the distance travelled, the hypotenuse. Well, actually, it's 3L, right? We've moved by 3L, okay, from start to end. Hopefully you're happy with that. So we can use SOHCAHTOA to work out h. So sine theta, again, is opposite h over hypotenuse 3L. Therefore, h is 3L lots of sine theta, but we also know sine theta is 5 over 13. So that's going to be 3L lots of 5 over 13, which will get me 15 over 13 lots of L. And there's my height. Okay. So I can sub that in. So that will go to 15 over 13 mgl. And that's my change in gravitational energy. Then lastly, the change in elastic energy. So remember, elastic energy has the formula lambda x squared over 2L. And in this case, my natural length is L. And my modulus of elasticity is kmg. So then the change in elastic energies, okay, again, final minus initial. Well, we look at the extensions we have, right? So at the end, the extension is 2L. So x is going to be 2L. So it's going to be kmg for lambda, lots of 2L for x, square that, divided by 2 lots of the natural length L. Then take away from the initial elastic energy. But as we discussed initially, in fact, there is no compression or extension because it's a string. So x is 0, okay? So it's going to be kmg lots of 0 squared over 2L. And hopefully you recognise that will all go to 0, okay? And so actually we just get left with this expression here. If we simplify, we're going to get 4L squared lots of kmg over 2L. And so that will simplify down to 2L of lots of kmg, or 2kmgl. And there we are. Right, and lastly, we need to look at the overall work on the particle, okay? So the overall work, what do I mean by that? I say it's the work forwards, take away the work backwards. So that is essentially the work done by any forward forces, and then take away the work done by any backward forces acting on the particle, okay? So in this case, what are the forward and the backward forces? Well, we ignore the sort of standard forces. So in this case, it's going to be tension and weight and the reaction force. Okay, because the tension and the weight, the tension is the elastic energy and the weight is the gravitational energy, right? That's included in the formula. So we ignore those forces, okay? So there is no forces acting forwards that we care about, okay? So there's no forward forces, there's no work done by any forward forces. But what about the backward forces? Well, you can probably guess there is a friction force which is acting backwards, okay, to the particle. So the friction is the backward force here. So we need to find the work done by the friction, okay? So remember, work done is force times distance, okay? Now, what is the distance travelled? Well, we already discussed it previously, but it's going to be 3L. That's how far we've moved from before to after, right? So that's my distance travelled. So it's going to be friction times 3L. So that goes to minus 3FL. But actually, we also know what friction is. Friction is 3 over 13 lots of mg. So I can sub that in. So this will all simplify to minus 9 over 13 mgl. Okay, and that's my overall work. And now I can sub everything into the work energy principle. So firstly, the change in kinetic energy, minus 3 mgl. Again, we keep the negatives, that's important. Then the gravitational energy is 15 over 13 mgl. And then the elastic energy change is 2k mgl, equals the overall work of minus 9 over 13 mgl. And so we can solve for k here. And actually, we can divide by the mgl to all the terms, get rid of all the mgls. So we just get minus 3, add 15 over 13, add 2k, equals minus 9 over 13. Then if I solve for k, well, 2k is going to be 3 minus 15 over 13 minus 9 over 13. So that would get me 2k to be 15 over 13. Then if I divide by 2, I get k to be 15 over 26. Okay, and that is what they wanted me to get to in part A. K is 15 over 26. Great. Okay, now in part B, I need to find the acceleration of the package at the instant it starts to move back down the plane from B. Okay, so I need to consider basically this situation here, where the particle's starting to, where it's at B, it's going to start to fall down. I'm going to redraw that situation, okay? The part B, so again, we've got this ramp. So we're at the point B, so the particle's all the way up here. The distance is 3L, okay? The natural length is L, so the extension is 2L. Okay, so this is point B. So we need to find the acceleration as it moves back down the plane. So the acceleration is going to act downwards. I'm going to call that A. Okay. Right, so again, we're not going to consider energy here because it's asking about acceleration. So acceleration, we're going to need F equals ma. So we're going to need to consider the forces now, not the energy. So let's label our forces. So of course there's going to be weight, okay, as always. So if we split the components up, that's mg cos theta, and then here by mg sine theta at theta. Okay, and then friction, as we discussed, the particle is going to move down the plane, okay? So the particle wants to move down. So if you think about it, friction opposes wherever you go. So if you want to go down the slope now, friction's going to act up the plane, up like that, to oppose you going down the plane. Hopefully happy with that, right? Because we're going downwards now. Now, obviously, the final force is tension. Because it's being stretched, okay, the string is being stretched currently because there's an extension. Now, again, strings oppose any stretching, okay? It doesn't like being stretched. So think about it. If it's being stretched forwards, there's going to be a tension force acting the other way to oppose the stretching forwards. So my tension force is going to act down like that, okay? And so there we are. So now, as I said, we're going to use F equals ma. So if we resolve parallel to the plane, so if we take down as positive because A is going downwards, the acceleration, well, my tension force is acting down, as is this mg sine theta. That's acting down the slope. But the friction is acting up the slope, so I'm going to need to take that away, and so that's going to equal ma, okay? And so then I can simplify this because I have t, but we know what sine theta is, so that's going to be mg lots of sine theta, which was 5 over 13, if you remember. Take away f, my friction. And also the friction is going to be the exact same as in part A, right? So we saw that the friction was 3/13 mg. Well, the reaction force hasn't changed, nor has the coefficient of friction. So friction will still remain 3/13 mg. So I don't need to spend more time reworking that out. So I can sub it in here. So 3/13 mg equals ma. Okay. So if I simplify this, I'm going to get T, and then if I add the mg's together, I have 5/13 mg, take away 3/13 mg, we get 2/13 mg equals ma. Now I need to find my tension force. How can I find the tension force? I can use Hooke's law. Okay. So remember that says that T is lambda x over L. So lambda is 15/26 mg. Then for x, what's my extension here? Well, hopefully you can see here where the extension is 2L, right? Because the total length is 3L, the natural length is L. So we've been stretched by 2L. So x is 2L. And then the natural length L. And so that will simplify to 15/13 mg. Okay. And that's my tension force. And now we can substitute that into my F equals ma equation. So therefore T, which is 15/13 mg, add 2/13 mg is ma. I can get rid of the m's, okay? So then I get A to just be 15/13 g, add 2/13 g. So if I collect all the g's, I therefore get my acceleration to be 17/13 g meters per second squared. And that is my acceleration there. Okay. We've got this final question here then. Now I'm not going to read the text here, but hopefully you can see we are dealing with an oblique collision question, a 2D collision question with walls. Okay. And so the first part of the question wants me to get this sort of expression here, okay, this weird expression. I'm not sure how to get to that, but I'm just going to do the normal process, what we do with collisions. So in this case, what I want to do is for the first collision here, okay, I want to consider my angles and my components. So I'm going to call this angle beta, let's say, afterwards. Then if I do the components like this, and also let's call the speed afterwards W, right? So if I do the components here, so that's so here, that's going to be V sine alpha. It's opposite the angle, so it's sine. And then parallel along the floor, it's going to be V cos alpha. And then afterwards, we're going to go along by W cos beta. And then upwards by W sine beta. Okay, hopefully happy with the components. So now what I want to do is if I consider, I want to do my equations, my parallel and perpendicular equations. So parallel for the first collision. So the parallel components remain the same. So those are the parts along the floor. So that's W cos beta is V cos alpha. Okay. Then if we look at the perpendicular part, next. So perpendicular to the wall, to the surface, it's going to be W sine beta and V sine alpha, right? Perpendicular. So they're going to differ by E. That's where E will act. So W sine beta is going to be E lots of the original component V sine alpha. And actually we know what E is, right? This is the wall AB, right? We're told the coefficient restitution with the wall AB is 2/3, okay? So actually we can say E is 2/3 there. And so what we can do now is, well, we're probably going to want to do tan, right? My answer has tan in, okay? Usually we just want to find tan of the angles anyway. Is usually what you want to do with these questions, regardless of what the question is asking. So if I call this equation 1 and 2, I'm going to want to divide the second one from the first one, because then that's going to get me tan, because I will get W sine beta over W cos beta to be 2/3 V sine alpha over V cos alpha. And so then I get tan, because sine over cos is tan. So therefore we get tan beta to be 2/3 lots of tan alpha. And that's my equation there. Okay, then I'm going to proceed to consider the next collision, which is going to happen here with the wall CD. This angle here then, well actually this angle's also going to be beta, because hopefully you can spot we have Z angles, right? We have a Z shape if I draw it here. Hopefully you can see that. So if I draw it over here, hopefully you can see even clearer, because this angle's beta, right? Hopefully you can see that here. We got alternate angles, so this is also beta there. Okay, hopefully you can see that. Again, think back to GCSE with your alternate angles, or like a Z shape like this, your Z angles. So the angle of approach is also beta here, right? If I do the components then, so we're going to go up like this and then across like that, and then afterwards we're going to go across and then down like that. So this component here, that's going to be W sine beta. Okay, W sine beta, it has the same speed W here, so W sine beta upwards, and then W cos beta along the surface, this surface here. Afterwards, I'm going to call the speed afterwards, the speed I'm going to call Z, let's say. So this part's going to be Z cos of a half alpha. Okay, and then this is going to be Z sine of a half alpha. Okay, so those are my components. So if I consider the parallel and the perpendicular equations for the second collision. So parallel. So firstly, the parallel parts is going to be along the wall. So Z cos of a half alpha is W cos beta. And then the perpendicular equation for the perpendicular components. So that's going to be these two here. So W sine beta and Z sine of a half alpha. That's again going to be affected by E. So Z sine of a half alpha is going to be E lots of the original W sine alpha. Okay. Beta. So there we are. Also, we know that E is 2/3 also with CD, with that wall there. So I can say E is 2/3. Okay, and there we are. So if I call this equation 3 and 4, again I want to divide them to get tan. So I'll divide the equations like this. I get Z sine of a half alpha over Z cos of a half alpha. It's going to be 2/3 W sine beta over W cos beta, and again we get tan. Okay, so therefore tan of a half alpha is going to be 2/3 tan beta, and there we are. Right, so that's all the equations I can gather, but we also know that tan beta is 2/3 of tan alpha, so I could sub that in for tan beta here. Okay, so I can say that tan of a half alpha is 2/3 of tan beta, but tan beta, as we said, is 2/3 tan alpha. So I can sub that in. So we get tan of a half alpha is 4/9 tan alpha. Okay, tan of a half alpha, 4/9 tan alpha. Right, how do we proceed here? Well, hopefully you can spot now we've got a sort of double angle situation, right? So we have alpha and we have a half alpha. So remember alpha is literally just 2 lots of half alpha, so we have a double angle, right? So I can use the I can think back to normal maths of how we can use double angle formulas and compound angle formulas for tan, right? So I'm going to need to go back to my formula book. So I'm going to be needing these trig identities, right? Okay, these are the compound angle formulas for sine, cos and tan. So as I said, I've got a double angle situation here with the alphas, right? I have half alpha and then alpha, right? Now I'm not given the formula for tan of 2, the double angle formula for tan, so I'm going to need to sort of derive it using the given formula, right? So tan of let's say 2 theta then. Okay, so A and B are going to be theta. If I substitute that in to the formula here, so tan of 2 theta for any double angle formula here, that's going to be tan theta plus tan theta over 1 minus tan squared theta. And actually that will simplify to 2 tan theta over 1 minus tan squared. Okay. And so in this case, okay, if we look at what we've got going on here, we can replace theta with a half alpha. So therefore we can say that tan alpha is going to be 2 tan of a half alpha over 1 minus tan squared of a half alpha. So now I have this expression for tan alpha, okay? So I can substitute that into this equation here, okay? I'm going to return back to the exam booklet, but there we are. We can use the formula in the formula book, okay? But again, you need to hopefully you're familiar with with how you can work with these double angle or formulas, okay, from normal maths. But there we are. Okay, so I've got this expression then for tan alpha from the formula book. So if I substitute it into here, then we're going to get that tan of a half alpha going to be 4 over 9 lots of 2 tan of a half alpha divided by 1 minus tan squared of a half alpha. Okay. So then if I times by the denominator, so I'm going to get tan of a half alpha lots of 1 minus tan squared of a half alpha is going to be 8 over 9 lots of tan of a half alpha. Okay, then if I factor everything out by tan of a half alpha, so then I'm going to get 1 minus tan squared of a half alpha, and then minus 8 over 9 equals 0. Okay, hopefully happy with that factorization there. I can simplify this a bit more, so then I'm going to get a 9th take away tan squared of a half alpha equals 0. So I can now solve for tan of a half alpha, so therefore tan of a half alpha is equal to 0, or the other bracket is 0. So that means tan squared of a half alpha is 1 over 9. Okay, and so if I root that, I therefore get that tan of a half alpha is either positive 1/3, right? If we root 1 over 9, we get 1 over 3, or we get the negative 1 over 3, right? If we do the negative root. Okay. So if we solve all of these equations then, so firstly, tan of a half alpha is 0, so that would mean a half alpha would be 0, right? So therefore alpha is 0. If we solve the second equation, if we do inverse tan of a third, we get half alpha to be 18.43. But then if we then to get alpha, we can times by 2, and then we get 36.9 to 3 significant figures. Okay. Then if we solve the last equation, we get half alpha to be minus 18.43. Then alpha is going to be minus 36.9. Okay. So we've got these three solutions then. We either got alpha is 0, alpha is 36.9, or minus 36.9. So to work out which solution to accept, we actually have a range of values, right? We are told alpha is between 0 and pi over 2. Now pi over 2 is 90, right, in degrees. Okay, so alpha is between 0 and 90. So which of my solutions are strictly between 0 and 90? Well, it's only going to, it's this one, right, the 36.9. So I'm going to say, but alpha is only between 0 and 90. Therefore, alpha can only be 36.9. Okay. So that's the only solution there. So I reject that one. I take that one and I reject that other one. Okay. So hopefully happy with that. Now, what did the question say? It wanted me to show that tan of half alpha is a third. Well, we actually already did that, right? So tan of half alpha is a third here, right? That's we got it from here. And actually tan theta can only be a third because that's the only equation here that produces my solution. So therefore, I'm just going to say that tan of half alpha is a third only. So we get we get that equation, right? And there we are. So then in part B, it says to find the percentage of the initial kinetic energy of the ball that is lost as a result of the two impacts. Okay, so now it wants me to find basically the loss in kinetic energy, or the percentage loss in energy. So the formula we use to find the loss in kinetic energy in collisions, okay, is always the kinetic energy before take away the kinetic energy after. Okay. Okay, so the kinetic energy before. Now again, remember, kinetic energy is a half mv squared. So the kinetic energy before all the collisions, right? So I'm talking about before the collisions. What was the speed before? It was v, right? So that's going to be half mv squared before. Then what about afterwards? Well, that's after all the collisions, right? So that's going to be, what's the speed at the end? It's the z, right? This z here, that's the speed at the end of the last collision, right? So there we are. So it's going to be half mz squared, okay, at the end. And there we are. So I can factor that out if you want to be a half m of v squared take away z squared. Therefore, the percentage loss in energy is going to be, well, the loss in kinetic energy out of the total energy we have, which is going to be the energy we had at the start, right? So the kinetic energy before, then times by 100 to get it as a percentage. And so I could substitute my results in. So loss in energy, we worked out to be a half m v squared take away z squared. And the kinetic energy before was half mv squared, right? Because v was my initial speed. And actually that cancels quite nicely to get v squared take away z squared over v squared times 100. Now, I am going to want to find a numerical answer to this. So I'm going to need to somehow get rid or solve for v and z, okay? So I want to find the speeds v and z. So the way we could do it, if I look at my equations, if I want to find the speeds, I would kind of normally square the equations, right, and get my speed that way. But I can just simply look at the equations, right? So I have z cos of a half alpha is w cos beta, but then also w cos beta is v cos alpha. So that gives me a link between z and v, right? So z cos of a half alpha is w cos beta. But we also know this is v cos alpha. So we can just cut the middleman and say that z cos of half alpha is v cos alpha. Okay, so we've got an equation with z and v, right? Which is all we really need. So obviously we have to deal with this cos of a half alpha and cos alpha. Right, okay. But if you think back to part A, we gathered that tan of half alpha is a third, right? So tan of a half alpha is a third. So what we can do again, we can use SOHCAHTOA, create a little triangle to deduce what cos of a half alpha will be, because that's what we want ultimately. We just want cos of a half alpha. We want an expression for that. So if I call this angle a half alpha, then again the opposite is 1 and the adjacent is 3, because tan is opposite over adjacent. Then the hypotenuse, 3 squared and 1 squared is 10, so it's root 10. Therefore we can deduce that cos of a half alpha is the adjacent over hypotenuse, so 3 over root 10. Okay, so I can say that this is going to be 3 over root 10. Now what about cos alpha? But actually, if we know that tan of a half alpha is a third, but we also saw in part A this equation here, right, that tan of half alpha is 4 over 9 tan alpha. So we can get tan alpha from this, okay? So we know that, that 4 over 9 tan alpha is tan of a half alpha, which is a third, okay? So if I just rearrange for tan alpha, so 4 over 9 tan alpha is a third, divide by 4 over 9, and we get 3 over 4, okay? And then we can do the same sort of triangle, right? So we have alpha now, and so the opposite length is 3 and the adjacent is 4. So Pythagoras tells me it's going to be 25, so root 25, which is 5, okay, for my hypotenuse there, okay. So therefore I can see that cos of alpha is going to be the adjacent 4 over hypotenuse 5. And there we are. So cos of alpha is 4 over 5. So 4 over 5 here. And so there we are. So now we get the equation simplified to 3 over root 10 lots of z to be 4 over 5v. And so I can rearrange for z by just dividing by 3 over root 10. So z on its own is going to be 4 root 10 over 15v. And actually, because if you look back at my fraction, I just want to find the square of it, okay? So if I square that now, so z squared, that's going to be 32 over 45v squared, and I can substitute that into my percentage, okay? So I can simplify this to v squared take away 32 over 45v squared for z squared, divide by v squared times by 100. So if I work all that out, okay, well the v squareds will cancel, so I'm going to get 1 to take away 32 over 45 times by 100, okay, because all the v squareds will go away, and so that will get me 260 over 9%, okay, because again we multiply by 100, or you could give that as a decimal, the 28.9% to 3 significant figures, okay. And there is my answer. So there's my percentage loss in kinetic energy. So there we are. So that's the paper. Hopefully that's helped. But I'll see you next time.